Hello again, everyone. Continuing with the theme of weird molecules, this time I want to focus on an element that everybody in the audience knows for sure. If you were able to read the title, congratulations. You passed the eye test.
Aluminum.
Aluminum is the second most produced metal in the world after iron, and it's a key component in electronics, vehicles, packaging, construction materials, gadgets, and many others. Now, let me take some time to tell you about its molecular properties, which you may not know as much of. Let's dive right in. Aluminum in its molecular form has 3 valence electrons. This means that it will form 3 covalent bonds by sharing those electrons. This also means that aluminum compounds will act as Lewis acids, which are also known as electron pair acceptors. Although the 3 plus is by far the most common oxidation state of aluminum, the +1 oxidation state has also been observed in a handful of compounds. Notable mentions are Schnockel's tetraaluminum cluster, which was reported in 1991, and this is a complex that exists as an equilibrium with the monomer at higher temperatures. This was followed by the report from Herbert Ruski from 2000, who reported the first monomeric aluminum complex shown here on the second structure. Thirdly, we have the first isolable cyclopentadienyl derived aluminum 1 monomer, which was reported in 2019 by the group of Braunschweig, and it features bulkier tert-butyl groups, which is the reason why they were able to isolate it as a monomer as opposed to the tetramer that Schnockel reported. And then most recently we have this bulky compound reported by Phil Power, which features another aluminum monomer, and this time being stabilized by a really bulky terphenyl group, which is this group here with the 3 benzene rings. Now, the compound that I want to talk about for this video is a compound that was reported by the group of Professor Ingo Krossing in 2022, and we can start here with the title. The first word, synthesis, that's pretty self-explanatory. Of a low valent, this means a compound of low oxidation state, in this case +1. Aluminum 4 cluster, which means a congregation of 4 aluminum atoms all bonded together, in this case a tetrahedral cluster. A cation, reference to a positively charged aluminum atom. And then a salt, because the compound is made up of a positively charged fragment and a negatively charged fragment, and so these two together form a salt. Now here's the molecule under discussion. As we can see, there is 4 aluminums in a cluster formation, but interestingly only 3 of them are supported by these steric groups. These steric groups are called pentamethyl cyclopentadienyl ligands, and they're very bulky anionic ligands that are used all over organometallic chemistry. And so the ligands themselves are very common. Here we have these 3 aluminums in the +1 oxidation state. However, because the top one is missing the cyclopentadienyl group, it could be considered a cationic naked aluminum 1 that's supported by these 3 aluminums. Now here is the space filling model of that same molecule, and we can see just how those CP ligands create a sort of crown around the aluminum 4 cluster, which then has those 3 aluminums directly bound to the CP ligands to directly stabilize the central cationic aluminum, which is on top here. Pretty cool. Now there's a few more things worth mentioning. Here's the paper. Um, the way they synthesize this compound is quite interesting because they start from Schnuckel's 1991 tetraaluminum compound, and they do a metathesis reaction with a lithium salt of a very bulky counter anion. They do this in fluorinated solvents, and they are able to form lithium cyclopentadienal, which precipitates out of solution, and then they end up with the compound at hand. Here's the crystal structure. Here's a few spectroscopic analysis. We have NMR showing the two signals for both aluminum types of atoms in the molecule. And then here we have a UV-Vis spectrum, both at room temperature and at low temperature, which shows that there is an equilibrium between a monomer and a dimer in solution. Another thing that's worth mentioning is the compound's very delicate, and this was based on the results that they obtained where upon leaving the compound to sit at room temperature for 12 hours in solution, they already saw noticeable decomposition to many compounds such as metallic aluminum, aluminum CP4 cluster like Schnuckels, and other aluminum 3 compounds. And in other instances, when the reactions were left for longer, they found other unknown decomposition products. So this is another compound that, despite being handled under an inert atmosphere of argon in the glove box, it's still delicate enough that it will decompose. And that's to no surprise. If we can see here, this cationic aluminum is quite unprotected and therefore very reactive. Here they show reactivity with Lewis bases, but that's beyond the scope of the video. And then they show the computational analysis of the electronic structure of that cationic aluminum. I hope you guys enjoyed this paper for today, and until next time.